Welcome to the talk, Secure Multi-Party Computation of the Differential Private Median. This is joint work with Professor Florian and Kerschbaum, and this work received funding from the Horizon 2020 EU program for the Mosaic Ground project. We begin with some motivation and preliminaries. Distributed private learning is a problem where parties with sensitive data want to learn statistics over their joint data while preserving privacy. There are many real-world examples. Differential privacy, for example, is used by Google to collect browser settings. Apple uses it for website resource consumption collection, and Microsoft uses it for telemetry data. Secure computation, a cryptographic tool, which we explain shortly, is used by Google MasterCard reportedly to perform ad conversion, meaning they track how online advertising leads to offline purchases. And there are different government studies like tax fraud detection and wage gaps. Our focus here is semi-honest users computing rank-based statistics, especially the median, with high accuracy, even for a small number of users, meaning small data, which is a tough problem for differential privacy, and strong privacy supporting large domains. Why are we using rank-based statistics, and especially the median? Well, first, we define what rank is. The rank of a value, we've got a data set, is its first position in the sorted data, if you use zero indexing. So given this data set, the value 2 has rank 3 because there are 3 values before it in the sorted data set. Notice that in duplicate, in this case, the element 1 has rank 1 because we use the first position. Rank-based statistics are versatile and robust, meaning it can be the minimum value, we can use it to define the maximum value, and in general, it can be any value with any rank, k-rank value, also called p percentile, including the median. The median is a typical value of data, which is more robust to outliers than the mean. We'll show what it means with an example. So if you look at the income in Medina, Washington, with a population of around 3,000, the median income is less than 200,000. However, the average income is much more than 1 billion. How can this be? Well, there are outliers in the data called Jeff Bezos and Bill Gates. That's due to the result. So the median here is more robust. Why are we using differential privacy? Well, we are considering private distributed learning, it's already in the name, and the median is one individual's value. There's no privacy, no aggregation even, as with some kind of sum statistics. And absolute differential privacy is a strong privacy guarantee and deployed by industry partners, and it bounds output differences if input changes in one record. And small epsilon corresponds to high privacy. We can achieve differential privacy by additive noise or the exponential mechanism. The exponential mechanism outputs an element m from the data domain with regards to some data set over that domain with probability proportional to the exponential function evaluated on epsilon times the utility of this value with regard to our data set. The utility for such a value, or the score, can be, in our case, the closeness to the median. We use the exponential mechanism as it provides better accuracy for the median. We evaluated the accuracy for different solutions of the differential private median computation and present an average absolute error of 100 rounds for those. There are solutions that can be computed with a trusted server. The exponential mechanism here highlighted as a black curve, which has the best accuracy. Smooth sensitivity, which also has great accuracy for a larger epsilon. And there are solutions without a trusted server, our work, here highlighted as blue, and a sample and aggregate-based version, highlighted in green. As you can see, the solution without a trusted server normally is a little bit worse. Our solution, however, is even better than the solution with a trusted server in the smooth sensitivity setting for low epsilon. Notice that we do not require any access to the data in the clear, unlike the solutions with trusted server. How can I achieve this? And, well, why do we want this? Well, why do we want secure multi-party computation is the question to ask here. There are different models to implement differential privacy. One model is local differential privacy, where different clients send randomized values to an untrusted server who outputs a randomized value. In this case, you do not need a trusted server, and unfortunately, you require large data for good accuracy. In the central model, clients send plain text values, and a trusted server applies the randomization only once and outputs the value. This achieves high accuracy, however, it requires a trusted server. MPC, where 3 or more parties jointly compute a function without revealing inputs using cryptographic tools, can do without a trusted server. It still achieves high accuracy, but the question is it efficient? Now we computed, or we combined the best of both worlds, but the question is it efficient? In general, no, because there's communication and computation overhead. However, we provide an efficient MPC protocol for the differential private median via the exponential mechanism. Recall, the exponential mechanism outputs a domain element m with probability proportional to the exponential function evaluated on epsilon multiplied with the utility for this value over a dataset D. How can we handle large domains if we have to compute the probability for each and every data domain element, as is the case with the median? Well, what we do is we divide the domain in subranges, and we iteratively select a subrange with the highest utility, thus achieving a runtime that is sublinear in the domain size instead of linear. How can we handle distributed data? Recall, we do not have a trusted third party, no central entity that has access to all of the data in clear. So how can we perform a distributed computation that still gives us the utility of all the data? Well, we use something called decomposable utility functions, as used in MapReduce style frameworks. Basically, we have a function, utility function, over the joint data can be expressed as a different function evaluated on the client data, and the sum of those evaluated functions gives us the utility of the joint data. Examples are simply counts and rank values, because rank can be expressed as count, mode and convex optimization in the context of empirical risk minimization. For details, I advise you read the paper. How can we manage the costly secure exponentiation? Well, we leverage decomposability again. In this case, we set U to be the utility of the already combined values and compute the exponential function for different epsilons. If we set epsilon to be ln of 2, we can simply compute 2 to the power of u, which is more efficient to compute an exponential function. And if we want to have a smaller epsilon, ln of 2 divided by 2 to the power of d, recall smaller epsilon means better privacy, we can express it as follows. First, we approximate the exponentiation by truncating it. Then we correct this approximation with a multiplicative term. This might seem more complex at first. However, there are more efficient tools provided by MPC protocols to actually compute these computations than a straightforward exponential function evaluation. And if we don't want to have any restriction on epsilon, what we can do is we let the parties compute their local utility over their client data. They multiply it by epsilon, and they perform the exponentiation themselves, and we simply multiply those values together. Recall the product rule for exponentiations. Multiplying exponents with the same base is equivalent to addition in exponents. Thus, we get the combined joint data utility. So how does this work step by step? First, we divide data domain into these different subranges. Then we repeat the following until the subranges are small. We evaluate, meaning we compute the local results, utility, and weight per subrange. Each client has a data set, and each client has rank values computed over those data set. And we can compute the local utility, since we know that the rank of subrange endpoints relative to the median's rank can give us a good utility base if the median comes before the current subrange, is contained in the current subrange, or comes afterwards, which gives us a sense of direction, and we can score the utility of the subrange accordingly. We combine these rank computations, recall they're simply counts, by adding them together, and then we select an output based on the weights we computed. This is done by inverse transform sampling and binary search. I refer to the paper for details. We use the selected subrange. We subdivide it again for the next iteration. And finally, in the last step, we output a random element from the last subrange. Now we come to the evaluation. we consider the running time in a wide area network with 100 milliseconds latency and 100 mbits bandwidth. Please note that LAN running time would be 10 to 60 seconds. However, to provide more realistic evaluation in a real-world setting, we show the wide area network running time here. We assume 1 million clients with one value each, using 3, 6, or 10 computation parties. Please note that 3 computation parties are sufficient. The clients can secret share their inputs with the computation parties who will run the computation on their behalf. We just show it to show how the computation overhead would increase if the clients choose to use more computation parties. So we iterate until the last subbranch has size 1, which is the largest number of iterations we perform, and evaluated 3 different weight computations. If we use an epsilon of L2 per iteration, you can tell that even for 1 billion records in 10 computation parties, we only require 4 minutes in a real-world setting. If we use a smaller epsilon per iteration, we require more minutes, 60 minutes in this case, for 10 parties, and less than 14 for 3 parties. If we put no restriction on the computation of the epsilon value, we achieve a running time of 20 minutes or less than 20 minutes for 10 parties, which is really great if you consider it's a one setting. And now for the conclusion, existing differential private median solutions with good accuracy require either large data or a trusted third party, or only support a small domain. Our contributions are high accuracy, even for small data and low epsilon, an efficient MPC protocol to achieve this via decomposable utility functions, which is independent of the data size, and we support large data domains using subranges. Thank you very much. I'm looking forward to your questions.